In solving homogeneous differential equations where the roots are identified as repeated and real, we have a specific solution for that. We have this in this form. Let me write it first. This is, of course, if we are sure that the roots are repeated and real. That's also part of our process later. But to write this first, our solution will be in this form. Your independent variable here, y, is equal to this form e to the power of mx. We're going to explain m later on, but x here is identified as our independent variable, and since it's not clear here, so it's okay to start or to assume x times c sub 1 plus c sub 2x, your again independent variable, plus dot 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 plus c sub n x to the power of n minus 1. We will have this solution later. The number of terms here will be dependent on a number of roots that are the number of times a certain root is repeated, and the number of this set is dependent on the number of roots with multiplicity. We'll have it later. Let's start by solving this equation now. We are lucky to have here an equation with already differential operator d. The goal here now is to come up with our auxiliary equation. So we'll have here m to the power of 4 minus 7m cubed plus 18m. So we simply change d to m squared minus 20m plus 8 is equal to 0. Okay, so this is a polynomial equation. We have m to the power of 4, so we are expected to have possibly 4 roots. Okay, yeah, 4 roots, but probably some of them are repeated as mentioned here. Now, we are going to check or solve these roots by, of course, factoring this if we can, but there are also some strategies that are implemented if we have polynomial equations just like this. We can use here a certain trial value that you could try here to solve for our solution. So we can always try here, let's say 1. Okay, let's start with 1. If m is equal to 1, if we substitute 1 here and this is equal to 0, then 1 is a root. And we can use the factor theorem for that to come up with another version of this right after we factor a certain one, a certain binomial. But of course, let's try. We have 1 to the power of 4. The suggestion here is, of course, to start with 1. Then if it's not, then we go to negative 1. If it's not, let's go to 2, negative 2, and so on and so forth. There are a lot of trial errors here, but of course, it will help us. Okay? But I'm also going to present here another method later once we are sure with 1 here. So 7 times 1 cubed plus 18 times 1 squared minus 20 times 1 plus 8, is it equal to 0? Let's try. 1 minus 7, because this is simply 1, plus 18 minus 20 plus 8, is it equal to 0? This is negative 27, 19, 27. Yes, that's correct. When we substitute 1 here, then 1 is a root according to the factor theorem. Okay, let's remove this. That means this is really an assurance that 1 is a root, and you can have a factor of m minus 1 is equal to 0. This is your first root. Thus, the other method I've mentioned is, of course, you can always use here the rational root or rational zero theorem, which tells us about a certain p over q possibilities. P are factors of your constant, so you will have 8, 4, 2, 1, including the negative, so plus minus, and you're going to divide this by the factors of your leading coefficient 1. So you will be having 1, 2, 3, 4 times 2, 8 possibilities, 8 types of trials, p over q, and this and 1 is included in here. You could try all of this here to find all the roots, and that's the rational root or rational zero theorem. You can use this, but since we're already sure with this one here, let's use the synthetic division to further simplify this. So synthetic division will use the division process, which can trim down this quartic into cubic. So the coefficients are 1, minus 7, positive 18, minus 20, positive 8, and your first root was 1. So 1 times 1, 1. Please leave your synthetic division for this. Minus 6, you will have 12, you have minus 8, and 0. This is an assurance. Once your remainder is 0, that's already an assurance, aside from this, that your root of 1 is really a root of the given. So once we are done with this synthetic division, you can have your cubic function m cubed minus 6m squared plus 12 m minus 8 is equal to 0. Then we repeat the process. You can use the factor theorem. The rational root 0 theorem together with the factor theorem, of course, or think other numbers. If we're going to use here 1 cubed minus 6 1 squared plus 12 times 1 minus 8. Of course, this is an odd number. It will not be equal to 0, right? If we're going to use here negative 1, so the cube of negative 1 is negative 1. The square of negative 1 is 1. So you have 6 times 1, the square of negative 1, plus 12 times negative 1 minus 8. This negative 1, this minus 7, of course, minus 12 minus 8, that's of course not equal to 0. So what we can try here, increase the possibilities. Let's try 2. When m is 2, so 2 cubed is 8, minus 6 times 4, which is 2 squared, plus 12 times 2 minus 8. Let's check if it's equal to 0. 8 minus 24 plus 24 minus 8. Obviously, that's 0. This is also 0. So 2 is the second root. Okay? So using that, our second factor is m minus 2 equal to 0. And again, using the standard division, you have 1 minus 6, 12 minus 8, and your second root was 2. So 1 times 2 is 2. Then you will have minus 4 times 2 minus 8. You'll have positive 4 times 2, positive 8, 0. Again, assurance. So this is now the second root. As you can see, our first root is 1. The second root is 2. We have not reached into a conclusion that our roots are really repeated, but they are both real. But we are not yet done. We have here the last form, m squared minus 4m plus 4 is equal to 0. And actually, this is a perfect square trinomial. You will have m minus 2, m minus 2 equal to 0. Or, easy way, a times c, 1 times 4 is 4. Factors of 4, when added, will result to minus 4. You will have negative 2 and negative 2. Because negative 2 times negative 2 is positive 4. Negative 2 plus negative 2 is negative 4. That's why you have here minus 2 and minus 2. And as you can see, aside from these two being repeated, it also has 3, multiplicity of 3. So, the bottom line here, our final set of factors, m minus 1 and 3, m minus 2. So, you will have here m minus 1, m minus 2, m minus 2, m minus 2 is equal to 0. These are the factors of this equivalent auxiliary equation. We're done with our roots, so let me just copy this. Let me copy this and copy, okay? And then paste that here for my guide of the solution. Okay. Bottom left, but yeah. Okay. Because we have our roots here. Our roots are, the first root is 1. The second root, m minus 2 equal to 0. Already have that earlier. So we can just automatically move into this. Second root is 2. The third root is also 2. And the fourth root is also 2. So we have 3, multiplicity of 3. Now, take a look at this. Of course, we can implement this solution for this. So you could have until the third element, third term here. However, we have here a root that is not repeated. Here comes some of the important notes that you need to really look at, because this is a combination of a root that is repeated 3 times and a distinct root aside from that. So we're going to combine here also the solution set for the distinct root. This is a solution set for distinct real roots. You will have c sub 1 e to the power of m sub 1x plus c sub 2 e to the power m sub 2x. But since we only have one type of root, so we'll have this first form. Okay? This will be our first form. So our final solution here is this. Why? Let's have 1. C sub 1 e to the power of 1x, or simply just equal to x. That's for the first root. Now for the second root, which is repeated 3 times, we will be using this. And since we already use c sub 1 here, this will not be c sub 1 anymore. Okay, it's okay. They are arbitrary constants. So we'll have here e to the power of your second root was 2x. This is the m here. Times C sub 2, again, we will not be using C sub 1, C sub 2 because we already used C sub 1 here. C sub 2 plus C sub 3x plus C sub 4x squared. Okay? C sub 2x squared, because that's what is the next term here. This is now our solution. Or if you would like to break this or distribute that, you will have y is equal to C sub 1 e to the power of x. That's for our first root. Then you will have here C sub 2 e to the power of 2x plus C sub 3x e to the power of 2x plus C sub 4 x squared e to the power of 2x. This will be confusing. That's why I always stick to this solution. This is our, it's already okay to have this. We have this for our first root, and this is our second root repeated 3 times. This is the answer to this given differential equation. Thank you very much for watching.